talking about Sobolev spaces, and we will talk about traces of function from H10. So as usual, we assume that omega is a bounded domain in Rn, and what is the motivation for this lecture? And why do we study Sobolev spaces in the PDE course? Because we want to talk about solutions of boundary value problems. And now the question is how we can understand boundary conditions if we're dealing with function from Sobolev spaces. Because we know that Sobolev spaces, their definition is based on L2 spaces. And if we have L2 functions in, say, Rn, and then we want to talk about their values on n-1 dimensional space, right? So set on the boundary, right? Then compared to our original space, this set would be set of measure 0. And if we are talking about L2 functions, if they differ on a set of measure 0, they still represent, only on a set of measure 0, they still represent the same element of the space. So, so what does it mean, value of a function from H10 on n-1 dimensional hypersurface? It could be anything. So just to to make sense of it, let's start with continuous function. Because for continuous functions in Rn, we can easily define values of this function on any hypersurface, right? Or surface in this n-1 dimension. And specifically, let's talk about function C0 infinity, right? So infinitely differentiable functions with compact support on omega. So the reason we want to talk about these functions first, because these functions are dense in H10, right? If you remember the definition of H10, it was the closure of C0 infinity in H1 or H10 norm. And moreover, when we talk about function, this infinitely differentiable function with compact support, we can easily, if we have a function given on omega, we can easily extend it into the entire space Rn by setting 0 values outside of domain omega. Right? So we can, if we have this, we can understand what this means. If we have a function this from C infinity with compact support, we can define their values on a hyperplane. So if we set one of our variables to be constant, and we will get this hyperplane, then we can define values of such a function just as restrictions on this hyperplane. So here I made a picture, so it is my Rn, this is our domain omega, and this is this hyperplane. And so this is our usual notation as we write restrictions, and I can call it T of u. And T of u I can call trace. So what is the conclusion? So for any function u from C0 infinity, we can define its trace, and it still will be C0 infinity, but on a space, if we're talking about hyperplane, on the space of or hypersurface, any on the space of codimension 1. And so we can think of T as a mapping from C0 infinity Rn to C0 infinity Rn minus 1. And we will see today that T can be extended as a continuous mapping from H10 omega to L2 and the intersection of omega with hyperplane. And also we can, our goal is to understand that we can think of C as a mapping from H10 on omega to L2 on D omega. But first, let's still talk about continuous functions. So our first theorem would be formulated for this continuous function. So assume that we have UK. UK is a sequence in C0 infinity, and UK is a Cauchy sequence in the norm H10. And then let's make this notation. Let's S be intersection of our omega with a hyperplane x, j, one of our coordinates, so j from 1 to n equals constant. And this intersection is not empty, but if we are thinking in this, so it will not be empty, right, if we extend our function. And then if we consider the sequence of traces, so it also will be a Cauchy sequence in the norm L2. And so we can write that if UM and UP, two members of the sequence, we can write that difference of traces in the norm L2S can be written as less or equal than constant times norm of these members of our sequence in H10 on omega. Let's go through the proof. So to prove this theorem, it's enough to prove this inequality, right? So as before in some previous our proofs, assume that we have a cube and omega is inside of this cube, and then let's consider a function u from C0 infinity on omega, and we continue our function u as 0 outside, right? So here u equals 0. So and this is our hyperplane and intersection S. And for this function, it's a smooth function, so we can use the fundamental theorem of calculus, so Newton-Leibniz formula. So we write this formula first, then we square both parts, so left hand side squared, here we have right hand side squared, and then we will use Cauchy-Bunyakovsky-Schwarz inequality as we done before. And so we assume that the integrand consists of the product includes the product of two functions 1 times this derivative, right? So then from 1 we'll have this integral, then derivative squared, and then from the first integral, if we, instead of integrating from negative a to c1, we will integrate from negative a to a. We will only increase it, so we'll have 2a here from the first integral, and in the second integral, if we replace c1 with a, since our function has complex support in omega, it will be the same integral. And then if we, instead of this first derivative with respect to x1, we will write a gradient modulus, absolute magnitude of the gradient, then we will only increase our integral. So, and then we integrate both parts of this one and this one. So we will have this inequality, integrate over S, over the intersection of omega with our hyperplane. And the right hand side, if we have integral over s and from negative a to a, so it will be dx1 dx hat, and x hat is here, it's all x's starting from x2 excluding x1. Then, so basically we have here dx, right? And then if we look now at this inequality, in the left hand side we have squared norm in L2 of function u, and in the right hand side it will be squared norm h1 0 norm. So we have this inequality. Here I just wrote in using different notations. So this is because this is the trace of function u on hyperplane S. So if we look, let's just look at this inequality, this formula. It's kind of good to know that we have such a formula. We will be able to use it later, right? So for any function u from c0 infinity, we have that norm of its trace, L2 norm of its trace is less or equal than constant times its norm, h1 0 norm on omega. And so now, just to finish the proof, let's replace u with this difference, um, up. And um and up, they both c0 infinity functions, and they are members of this sequence uk. And then, if we go back to this inequality and replace u with the difference, we will have um at c1 x hat minus up at c1 x hat, this norm squared, less or equal than to a, and the difference of these functions and in the norm h1 0. So, and if we have this inequality, it means if we just replace notations, we will end up with the inequality that we wanted to obtain. This finishes the proof. Let's talk a little bit more about this theorem. So what we can gain from it. So the theorem was talking about a function from c0 infinity. So now, what was the definition of function from h1 0? Right? It's we say that u belongs to h1 0 on omega. It means that exists a sequence of function uk from c0 infinity such that in the norm of h1 or h1 0, the equivalent, this norm goes to 0 as k goes to infinity. So now, in this theorem, uk is a Cauchy sequence, right? So this norm and h1 0 omega goes to 0 as p goes to infinity. And what we have from this theorem, right, from this, that the sequence of traces, I put here 3 different notations for the same sequence. So the sequence of traces is a Cauchy sequence in L2. And as a Cauchy sequence, it has the limit. And so it converges to some element of L2. And this element we can call u, say s, or t of u, so it's just a notation. And converges means that norm in L2 goes to 0 as k goes to infinity. Here I again wrote it in different notations. So here, so far, it is just a notation, right? It's an element, the element to which this sequence converges. And now we can call this element the trace of function u from h1, 0 on the hyperplane. Let's continue studying traces. So theorem 2, assuming that the previous theorem was theorem 1, the trace of function u from h1, 0 on the hyperplane continuously depends, xj equals cj continuously depends on cj. So to see that, let's consider a sequence of function from c0 infinity, and such that it converges to in the norm h1, 0 to an element u. And then let's again take as xj, take x1 and consider two planes. The plane x1 equals c1 and the plane x1 equals c1 plus delta x1. And traces of our functions um would converge to the traces u c1 of u at c1 x hat as before all other x's, and to the trace of function u, so it will be written as u at c1 plus delta x1 x in the norm L2 in this -1 dimensional space. And as before, we will write fundamental theorem of calculus for this difference, and as before, we will square both parts and use Cauchy-Bunyakovsky-Schwarz to the right hand side by splitting this into the product of two integrals. From the first integral we'll get delta x1, from the second squared derivative. And then, as before, we assume that our domain omega is in a cube and functions um are continued as with zero functions, and then if we will just increase the interval, we will get something only bigger, and then we will integrate both parts. So in the left hand side we have this, we integrate over s, so we'll have this integral, and in the right hand side then we will have integral over omega. And if we replace this first derivative with the magnitude of the gradient, we will make it even bigger, and magnitude of the gradient will give us this norm squared times delta x1, which we had before. And then we will take a limit when m goes to infinity. Then if we look at the left hand side, instead of um we can write u now, and in the right hand side we know that um converges. It's a convergent sequence, so it is bounded. So we can find here a constant, we call it constant m, so here we'll have m delta x1. And so what we can see from this inequality, that when delta x approaches 0, then the left hand side also will go to 0, which gives us the continuous dependence on C1. So so this finishes the proof. So to summarize what we discussed so far, that if we take a function u from h1, 0, this function defines another function trace of u, which is element of L2 on any hyperplane, and moreover we just shown that this trace continuously depends on the hyperplane. So far we've been talking about traces on hyperplanes. But what if our S is not planar? What if it's a smooth hypersurface? Then we can basically repeat everything that we said for hyperplanes. So, for instance, we will be talking about the kind of a piece of hyperplane that is defined by this equation, and phi is C1. And so here I made the picture. It's our omega. This is our cube that contains our omega, and we will continue of the function as 0 outside. And so this is our S hypersurface, and this is its projection, right? D. And as in Theorem 1, we can consider a sequence of functions in C0 infinity, and we can take two elements of this sequence and write a fundamental theorem of calculus using Leibniz formula. And as before, so the only difference compared to the Theorem 1, instead of C1, we will have here phi, right? X1 will be not constant but function of all other variables. And then, as before, we can square both parts and use Cauchy-Bunyakovsky-Schwarz inequality, right? And then we integrate over S. But to integrate over S, we multiply by this expression and integrate over D. And so we have it written here. And then in the left-hand side, we can write it as integral over S of this expression. And in the right-hand side, we can pull out maximum of absolute value of this term, and we call it M of phi, and the rest would be integral over omega of the magnitude squared of the gradient. And so what we have in the left hand side, we have norm in L2, and in the right hand side we have norm in H10 times a constant. So theorem 1 can be repeated for hypersurfaces, so we can give a similar meaning to the trace on a hypersurface. And now, having this in mind, we can describe another property of the space H10, because for any function H10, trace on its boundary will be 0. Indeed, we can think of function u as the limit of the sequence of function from C0 infinity, and all of them have 0 value on the boundary. Okay, so let's make another comment about correctness of our definition of traces. So we define traces using sequences of functions from C0 infinity. And what if we take two different sequences that converge to our function in H10, but what if they will have different traces? So let's show that this is not the case. So we consider function u from H10 of omega, and let's take two sequences um and uk tilde sequences, and their elements are functions from C0 infinity. and both sequences converge to our function u in the norm h1, 0. So now consider two sequences of traces. So TUM and TUK tilde on our hypersurface S. And we know that both converge, and let's say that TUM converges to TU and TUK tilde converges to TU tilde in L2. And here I just wrote another notation just for you to remember that we use different notations. So our claim is that TU and TU tilde coincide almost everywhere, so as elements of L2 on S. And to show this, let's take the norm of the difference of these two in L2 on S, and let's use a triangle inequality. So we can go from U to UM, from UM to UK tilde, from UK tilde to U tilde. Right? So this is a triangle inequality. And then let's recall that from our first theorem we had that if we have, for some sequence, if we have UM and UP, say two elements of a sequence, then difference of their traces in L2 norm on S is less or equal than the constant and times norm of the difference in H1, 0. So we had this inequality today. So now let's see that from this inequality, if we fix M and send P to infinity, we can get another inequality, right? Which we will use now for every term in the right-hand side. So here I just copied the left-hand side, and then from this, using this inequality, we can say that each norm, L2 norm in the right-hand side, we can estimate as H1, 0 norm. So we will have again U minus UM in H1, 0 norm, UM minus UK tilde, H1, 0 norm, and the last one. And so now we have this, and we can take a limit when M and K goes to infinity. When M and K goes to infinity, then every term in the right-hand side will go to 0. So we will see that the left-hand side is also 0. So this difference is 0. L2 norm of this difference is 0. So it means that the elements coincide and our definition of traces was correct. That finishes the proof, and thank you.